so we're looking at discussion question 3.11. It says uniform circular motion. How does the acceleration change if the speed is increased by a factor of 3? So what we're going to do here is we are going to be looking at this equation right here. And how do I change V, and then what does that do to AC? So what we're looking at is if I, what did they say, double or triple? The first one, triple. So if I multiply the velocity by 3 here, essentially what have I multiplied this side of the equation by? Well, it's 3 squared. So essentially I multiplied this side of the equation by 9. So that means I need to do the same thing over here. So it would be 9 times the acceleration if I triple the speed. And so then you can go ahead and say, well, what if I double the speed here? So if I double the speed, that would be 2 squared. That would be 4 times the acceleration, and so on and so forth. So what we're going to do now is we're going to flip over here to Socrative. So go ahead and go to Socrative. You're going to go into the room, I believe it's Foster 217 AP. And you're going to do 1 and 2. Once you have those two done, come back and I'll explain them for you. All right, so now you've done those Socratives. So a child's standing, rotating carousel, and we do half the radius, but the period stays the same. So we have half the radius, but the period stays the same. So essentially I divided the right side of the equation by 2, so I need to divide the right side by 2. So it'll have half the acceleration. Next, the object is moving at a constant speed. Now, constant speed and constant period are different things, so let's keep that in mind. And so for number 2, they wanted to go ahead and double the radius and double the velocity. Oops. So if I double the radius and double the velocity, but remember, velocity is squared. So essentially I have it multiplied by 4 on top and divided by 2. So 4 divided by 2 means I've doubled the acceleration. And there you go. So we're going to do this example. So the Earth has a radius of 6,380 kilometers. We'll have to change that to meters. And turns around once on its axis every 24 hours. So that's the period. We'll have to put that in seconds. Now it wants to know what is the radial acceleration of the object at the Earth's equator. So if I want to find the radial acceleration or the centripetal acceleration, they're synonymous with one another. What I'm going to need to do is I'm going to need to go ahead and combine the centripetal acceleration equation and the speed equation so that I can have the centripetal acceleration dependent on period. Once I do that, I can go ahead, plug in my numbers here, and I get 0.01 meters per second squared, which is a pretty small number. Now they also want it as a fraction of g, so to get that I do 0.01 divided by 9.8, and you can see we get a very small number there. 0.001 Gs. So 0.1% of the gravitational acceleration is used to go ahead and find to make you go around in a circle. The rest of it's holding you to the Earth. Now as you go up along the Earth toward the poles, either way actually, your radius from the axis of rotation actually shrinks. And so your centripetal acceleration becomes 0 at the 2 poles. And it's a maximum at the equator. This actually works out kind of funny that you actually have an apparent weight that is less at the equator than you do at the poles by a pretty small fraction. Okay, now it wants to know, well, what's the maximum speed, or what would the period of the Earth be so that the Earth's rotation would have be so fast that you fly off into space. Okay, so the most gravity can supply is 9.8 meters per second squared. Any more than that, and gravity can't make you go in a circle. Okay, so we're going to go ahead, plug that information in here, and you get a period of 2860 seconds, or 47.7 minutes. So if a day was only 47.7 minutes long, we would essentially be weightless at the equator, but you'd weigh your full weight at the poles, and any with the equator, if it went any faster, would just kind of fly off, or if they jumped, they just wouldn't come back, type of thing. So you'd have to be very careful at the equator, but life would be normal at the poles. There we go.